talk in our session this afternoon. We have Xuwen Tao, and the talk is, you got two of you. We have two authors on this paper. And so continuing in our sequential recommendation theme here, we are looking at task-aware feature extraction. And this is a paper kind of about multi-step tasks and using the structure of multi-step conversion tasks. Okay.
Hello everyone. We come from my bank and group. The presentation this afternoon is introduced by my colleague and me. In this work, we will concern primarily multitask learning with sequential dependency constraints and how to extract implicit shared message and explicit task-specific information. Our talk will be in 4 parts. To begin with, I'll be speaking about the background of the multitask learning and discussing formulate the definition of the sequential dependency multitask learning problem. Then, we will introduce the proposed framework. After that, we'll provide and discuss the performance of the present theoretical and implement frameworks by lots of experimental results. And finally, we will summarize this work. The most common application of multitask learning in recommendation systems is multi-step conversion estimations in the display advertising, financial service, and so on. CTR, CVR, and CT-CVR estimations are a series of classical tasks with sequential dependence in the customer acquisition process. The multi-step estimation problem is a typical multitask learning with sequential dependence. Here, we call it SDMTL. As shown in this figure, a conversion example in financial service strictly follows this sequential dependence pattern. A user's conversion process of financial products starts from impression, then click, authorize, and finally apply loans or purchase investment products. In addition, previous works have mostly focused on CTR and CVR estimations. However, there are rare works to provide a formalized definition of the SDMTL problem. It is particularly significant in multi-step conversion estimations for more diverse scenarios. Besides, the connection and the difference between the general MTL and the SDMTL is also unclear. On the other hand, the information passing mechanism among tasks is also a particularly noteworthy problem. Improper feature sharing will result in the poor or imbalanced model performance. General MTL frameworks mainly focus on designing various kinds of experts to learn common and task-specific representation. The performance of SDMTL framework is also deteriorated by the interference derived from conflict information passing among tasks. We will introduce how we address this problem in the following parts. Consider an SDMTL problem over an input space X and a set of task Ti, where n is the number of tasks, not data set of points are given. M is the number of data points. OIJ is the label of the task for the data point. Differing from the general MTL problem, there is a sequential dependency relationship among tasks for the SDMTL problem. In the sense that the current task Ti depends on the previous tasks. For the sequential dependency, one of the core properties is that if the event Ti-1 is not triggered, then the event Ti must not occur. Intuitively, the probabilities of the adjacent tasks satisfy following inequalities. Actually, in this work, we found that the dependency relation between the adjacent tasks satisfy a more accurate equation relationship. Similar to the general MTL problem and according to the dependency relationship, the objective of SDMTL is to minimize the following expected loss. With this operation, the sequential dependency relationships can be effectively used to further improve the performance of the MTL frameworks, which enable the general MTL models to solve the SDMTL problem. Next, the following parts are introduced by my colleague.
Okay, to address the issues of the model structure, we proposed a framework consisting of 3 core parts. It's worth mentioning that our model abandons the traditional approach of using expert groups of MLPs. Instead, we adopt a fully attention-based structure. It's a feature interaction method for CTR estimation. And it has shown great performance in extracting feature interaction information. The first part is adaptive sample-wise representation generator. We call it ASRG. It's used to extract shared information among tasks. To avoid noise propagation between tasks, we also design a dynamic activation layer. And the second part is task-specific adapter. We call it TSA as its name. It can extract task-specific information. And then the shared and specific information are combined, input into the final output layer. The third part is the loss function designed by my colleague mentioned, which contains sequential dependency between tasks. Unlike the traditional approach of designing different losses for each task and summing them, our loss function can provide more supervision signals. Next, let's take a detailed look at the extraction of shared information. First, features from different fields are transformed into lookup embedding layer. Instead of using the traditional self-attention model, we randomly initialize a matrix as query, where the number of rows is a hyperparameter, usually smaller than the number of fields. The reason for using this type of query is to reduce computational and introduce our dynamic activation module. We have also tried the direct application of self-attention and found that there is no significant difference in accuracy, and the computational cost is reduced. Because in our industry scenario, the number of feature fields is large. It's close to 3,000. Then the key and value are obtained in the same way as self-attention. From this formula, we can see that each row of vector of the query can be seen as extracting a feature information, which we call a feature pattern. If the number of rows is n, then n patterns are extracted. However, not all n patterns are used as shared information to enter the final output layer. They need to go through a sample-wise filter called the dynamic activation layer. The main purpose of this layer is to learn a binary mask vector with values 0 or 1 for each sample to determine which feature patterns should be shared and which ones should be considered as noise. The mathematical implementation is to apply the learned I vector and multiply it by the query. Okay, there are many ways to achieve the dynamic activation layer goal. Let me introduce the method we used. Our way is simple. First, we input the features into an MLP, and the activation function used is shown in this figure, which is a three-stage function. The middle stage is a third polynomial, and its gamma parameter is not a fixed hyperparameter, but a value that decreases with the training steps. As the training steps increases, it collapses into a step function, as this shown. Then the output of this network is a binary vector. The network TSA is designed to extract task-specific information. It's also based on attention, but it's much more simple than ASRG. Each task has a TSA network. Here, the query is also randomly initialized, and we call it task indicator. The key and value also come from the feature input. Through experiments, we found that a single row vector of the task indicator can achieve good results. Then we combine shared information, ASRG via an add normal operation. Finally, we obtain the task we're embedding, then passed through a shadow MLP to obtain the final predicted output label. The final step of this framework is to determine how to train this model with the loss function. Traditional multitask networks such as MMOE and PLE did not consider sequential dependency between tasks, so their loss function simply sums the losses of several tasks. Since we have already provided a theoretical definition for sequential dependency, we can design a loss function that combines dependency information based on the serial. As shown in this slider, for example, if task I-1 is click and task I is conversion, we are the loss between the predicted and the true values of click minus conversion. The experiment used two datasets, RecCCP and our industrial dataset. The train evaluation test split of the industrial dataset is based on the time of the data. The evaluation metrics we used are gain CTR and gain CTCVR as shown in this figure. The experiment showed that our method outperforms these traditional methods, both on open source dataset and industrial dataset. Furthermore, ablation experiments showed that each module of our method has a certain impact on the final result. Additionally, we did more experiments on the loss. We reused this loss in some traditional methods, such as MMOE and AITM. We found that this method, when combined with our loss, also achieve improved performance compared to the raw visions. Next, we conduct a more in-depth analysis of the dynamic activation layer. We plot the distribution of non-zero rate of the mask vector. And we found that it's followed a normal distribution. This indicates that some sample needs less shared information, and some needs more. We also select top, mid, tier 500 data points to reduce the dimension and draw this picture. And we can see that the three types of points cluster separately. This confirms this layer has learned the attributes of each sample. Furthermore, we analyzed the model performance in terms of runtime and storage. Our method showed little difference from other traditional models in both aspects, indicating that it does not need additional storage or computational costs, even it has the lowest storage occupation. Online experiments conducted in an industrial environment. Our industrial environment is a financial scenario. And the results in the online experiment also proved the great performance of our method. In a week-long A/B test, TFE has always outperformed the MMOE model. The MMOE model is deployed online as our baseline for a long time. And now in our online system, TFE has fully covered. So conclusion, we do three things. We proposed a new SDMTL paradigm, and we proposed a TFE framework to solve some problems. And finally, we do offline and online experiments to prove its performance. Okay, thank you very much.
All right, we have some time for questions. Come up to the microphones here.
Hello. Hello. What is the biggest problem you think this model in practice application? Thank you.
Okay, you mean the biggest problem we have made? Yes. I think in our online practice, the biggest problem of this model compared to other methods is that the number of hyperparameters is large, such as we just said such as the number of rows of queries or the layer of self-attention and some hyperparameters for TSA networks, and finally the loss function. So there is a lot of hyperparameters. So it makes it hard to make the model tuning work in our online practice. And in our online practice, we also find another problem, but not a big problem. Is in our method, when the number of feature fields is large, it can achieve a good performance. But the number of feature fields is small. It shows no advantages over the other methods. But it's not a problem in our industrial scenario, because in our industrial scenario, the number of feature fields is very, very big. So maybe it's a problem for open source dataset. Yes. Thank you for your question.
So there was a question on Slido, and basically the question was if you could describe what the actual recommendation application is for your online experiments, like what's being recommended in what context. You're predicting the next task, but how are you actually using that for recommendation?
You mean in our industry scenario?
Yeah.
Yes.
Yeah.
In our industry scenario, our industry scenario is not a traditional recommender system. Actually, it's a marketing system. So what we do in our daily work is such as we select some people from all of our customers and select someone to push some advertising. Mm-hmm. And so this pushing should be according to their CTR or CVR scores. So the CTR and the CVR estimation is very important in our industry scenario. And in our online experiments, we found that the CTR and the CVR scores get from our method. The people chosen by our method is better than the traditional methods.
Okay, so I'd still call that recommendation, right? But it's a push, kind of a push recommendation. My question I had, see anybody else out there? Yeah, so question that I had, I'm wondering how much this method is tied to sort of a linear structure of the sort of subtasks, or whether you could handle a more, kind of complex structure. So for example, maybe my one way to get to the purchase is I click on the web page, but another way to get to the purchase is I get a marketing email and I respond to that, or there might be multiple multiple touch points basically that contribute to the task. I mean, if you go back to the earlier part where you're sort of setting up the problem. Yeah, here, right? So what if there's impression, click, authorization, there's also email, or there's in-store, interaction or something. There might be a variety of different task structures. And does the model kind of assume that it's just one, linear sequence of steps?
Generally, the impression seems like advertising, 就是 a user is explore some advertisement, then he may click this sort of advertisement. In financial products, authorization is necessary.
Sure.
Then the user maybe apply the loans or purchase the financial products.
Right.
Which implies that the conversion path is different from the CTR or CVR. The traditional CTR or CVR conversion, maybe it has more various conversion paths. Therefore, we focus on the sequential dependence between the adjacent tasks. Then, a systematical multitask learning with sequential dependence constraints. Problem is formula is defined. Yeah.
But it seems like it has to be step A, step B, step C, as opposed to A1 leads to B, A2 also leads to B, A3 leads to B, kind of multiple dependencies like this.
There are various conversion paths. For example, step A to step B or to step C. That is then the other example is branch. It's branch dependency relationships. Till now, we consider the sequential dependency as step A to step B.
Right, so more linear.
Yeah. Our future work is concerning more various.
More structure.
Passes.
All right, interesting. I think our time is up. I am supposed to tell you that if you would like to walk together to the banquet, there will be groups leaving here in front of registration at 6 and 6:15. And so you can come here and then you'll be able to join with the other conference attendees and walk to the banquet site. And thank you for your attendance. We'll see you tomorrow.